Here's a belief that quietly wrecks machine learning projects. That the model does all the work, so you just throw the raw data in and let it sort things out. It doesn't work like that. Garbage in, garbage out isn't a slogan. It's the law. The features you build set the ceiling on how good the model can ever get. The model only fits what you give it. So let's learn the craft that actually decides quality. Feature engineering. Here's the whole idea on one screen. On the left, raw messy data, mixed types, wildly different scales, a date, some text, a category. In the middle, a handful of transforms. Scale, encode, bin, extract, combine. Out the right comes a clean feature matrix. Tidy numbers, all on one footing. And look at the bottom. On raw inputs, the classes are tangled and there's nothing clean to cut. But once the features are right, the model can finally draw a straight, confident boundary. Same data, transformed well. That's the craft. Chapter 1. Why better features beat a fancier model? Take one dataset and run the experiment. Feed the raw inputs to a fancy, powerful model, and it claws at a tangled boundary, overfitting the noise, never quite separating the classes. Now feed engineered features to a plain, simple model. Watch the boundary snap straight. The simple model on great features cuts cleanly, and it wins. The transform did the heavy lifting, not the algorithm. This isn't a one-off. It's the pattern across almost every real project. Teams burn weeks chasing a fancier architecture for a couple of points, when a single well-built feature would have moved the needle far more. The reason is blunt. The model can only fit what you give it. An algorithm cannot recover signal that isn't in the inputs. No amount of depth or parameters conjures information that was never there. Expose the right signal through good features, and even a humble linear model shines. Hide it in raw, unscaled, untranslated columns, and the fanciest model loses. That's why, over and over, better features beat bigger models. Chapter 2. Numeric features, scaling, and shape. Start with plain numbers and watch the scale block light up. In our raw table, income is in the tens of thousands, while age is in the tens. To a model that measures distance, or one that learns by gradient steps, income would completely drown out age. So you scale. Standardize every feature to mean 0 and variance 1, or squeeze it into a 0 to 1 range with min-max. Now no feature shouts over the others. One important caveat. This matters for distance-based and gradient-based models. Decision trees split one feature at a time, so they genuinely don't care about scale. Two more numeric moves earn their keep. First, the log transform. Something like income or price has a long heavy tail, a handful of huge values stretching everything out. Take its logarithm, and that lopsided spread becomes smooth and roughly symmetric, which most models handle far better. Second, binning. Slice a continuous number into ranges. Turn age into child, adult, senior, and the model can latch onto a threshold effect it would otherwise smear across a single straight line. The theme tying both together. You're not adding information, you're reshaping it into a form the math can actually use. Chapter 3. Categorical features. Turning labels into numbers. Now the encode block lights up. A model can't read the word Pune or Mumbai. It needs numbers. The honest default is one-hot encoding. Give each category its very own column that's 1 when present and 0 otherwise. City equals Pune becomes a 1 in the Pune column and zeros everywhere else. It's clean, and crucially, it imposes no fake ordering. Pune isn't somehow greater than Mumbai. This works beautifully, right up until the categories explode. Here's the high-cardinality trap. One-hot encodes something like 50,000 zip codes, and you've just created 50,000 mostly empty columns, a sparse, bloated mess that slows training and invites overfitting. The fix is target encoding, sometimes called mean encoding. Replace each category with the average outcome for that category. 50,000 columns collapse back into one informative number. It's powerful, but there's a catch. Compute that average using training data only. Peek at the rest, and you've leaked the answer, which is exactly the trap we hit in Chapter 5. Chapter 4. Dates, text, and interactions. Some columns are useless until you crack them open, and that's the extract block. Take a raw timestamp, like a sign-up date. As a single number, it tells a model almost nothing. So decompose it. Pull out day of week, hour of day, month, and a simple sweekend flag. Suddenly the model can see that weekend behavior differs from weekday behavior, or that something spikes every evening. One timestamp was hiding a dozen useful features all along. 2 more. Text can't go into a model as a raw string, so turn it into numbers. At the simplest, counts of each word, and at the richer end, a dense embedding vector that captures meaning. And then there are feature crosses, or interactions. City on its own might say little. Hour of day on its own might say little. But city multiplied by hour can expose a sharp pattern. Busy downtown at 6 in the evening behaves nothing like a quiet suburb at noon. Crosses surface signal that lives only in the combination. Chapter 5. Leakage. The silent killer. This is the mistake that fools even experienced teams. Look at the dataset, split into train and test. Watch what happens if you fit your scalar, or any transform, on the whole dataset before the split. The scalar peaks at the test rows to compute its mean and range, and the test set quietly bleeds into training. Now watch the fix. Fit the transform on the training data alone, then apply it to the test set. The test set stays genuinely unseen. Leakage, in one line, is using information at training time that won't be available at prediction time. Leakage wears two faces. 1. A feature from the future. A value that only becomes known after the moment you'd actually predict. 2. A feature that secretly encodes the target. A column that is, in disguise, the answer. Both make your offline score gleam, 99%, flawless, and then collapse the instant the model hits production, because that information simply isn't there at prediction time. So treat a too good to be true score as a red flag and hunt leakage relentlessly. Fitting that scalar before the split is the classic culprit. Chapter 6. Domain knowledge. The real edge. Here's the part no library can do for you. The very best features come from understanding the problem. Take a raw column of transactions. An automatic tool sees numbers. An expert sees a question worth asking. Like, how does today's spend compare to this customer's own 30-day average? That single crafted ratio can carry more signal than 100 raw columns. Recency, trends, meaningful ratios. The things a domain expert would actually look at. That knowledge is the moat. Chapter 7. A worked example and a deeper look at leakage. Let's put one idea to work end to end. Grab the sign-up value from our raw table, a single timestamp. As one running number, it's useless. Every later row is just a bigger integer, so the model sees no pattern in it at all. So we send it through the extract block and crack it open. Watch 4 real columns drop into the feature matrix. Hour of day, day of week, an weekend flag, and time since the last event. Now the model can finally see that weekend signups behave differently, or that activity spikes every evening. And look at the bottom. As those columns land, the boundary straightens. Same date, 4 features, a cleaner cut. Now leakage at its most dangerous. A feature that secretly is the answer. Say you're predicting which customers will churn, and you slip in a refund issued flag. The catch: a refund only gets filed after someone has already cancelled. So at training time, that column lines up perfectly with churn, and your offline score looks flawless, 99%. In production, at the moment you actually predict, no refund exists yet. The column is blank, and the model is lost. How do you spot it? When one feature carries almost all the importance, and the score looks too good to be true, get suspicious. Ask whether that value truly exists before the prediction. If it doesn't, drop the column and recheck. Let's trace the whole pipeline one last time and watch the boundaries straighten as we go. Scale and log your numbers. So distance and gradient-based models behave. One-hot the small categories and target encode the big ones to dodge the high-cardinality trap. Decompose dates, embed text, and cross features to surface hidden signal, and fit every transform on the training data only, so nothing leaks. Raw to transform, to clean features, to a boundary the model can finally draw. So here's the takeaway that quietly separates good practitioners from the rest. Don't reach first for a bigger, fancier model. Reach for better inputs, scaling, and logs so distances behave, encodings for your categories, decompose dates and text, crosses that expose signal, and a relentless guard against leakage. And above all, domain knowledge. Features often matter more than the model because the features set the ceiling and the model only reaches for it. Better features beat bigger models. Subscribe for more such intuitive videos.